Welcome to my presentation. I will talk about a vulnerability I found in a forensic tool that a suspect can use to potentially run arbitrary code on a forensic investigator's machine. First, who am I? My name is Wolfgang Ettlinger. I'm a security consultant at SecConsult, and also at SecConsult I'm an active contributor to the SecConsult Vulnerability Lab. This is the White Hat Security Vulnerability Research Division of SecConsult, where we actively look for vulnerabilities in software products and do responsible disclosure to try to get them fixed. Since 2003, we have published over 200 security advisories, and in the last couple of years we have had these main points of topic points that we were interested in, so IoT, hardware hacking, also security software and e-government. The purpose of the Vulnerability Lab is to improve security of our customers and also of ourselves by looking at tools that we use ourselves, and through responsible disclosure get those vulnerabilities fixed, and therefore by extension help everyone improve their security. One of those tools that we use ourselves in forensic investigations is Enkes Forensic Imager. Enkes Forensic Imager is a tool that can be used to gather evidence, gather images from evidence. So if you have a hard disk or a flash drive, or also want to create an image from a physical memory, you would use this tool to create an image and then analyze this image instead of the actual evidence. And the idea of the Enkes Forensic Imager is this is a slimmed down version of the commercial ENSIG forensic suite. The idea is that if you don't have the Enkes forensic suite available, which requires a license and all, you can use this free tool to simply create an image, which can later then be analyzed using the full forensic suite. And apparently a lot of code is shared between those two products. So in order to find vulnerabilities, we implemented our own fuzzer in Python. So we implemented generators for all sorts of different file disk formats. For example, FAT32, LVM, X3, MBR, GPT, so partition tables. And we then used the fuzzer to generate those disk images, but modify some of these values. So for example, we would replace strings with long strings, or replace integers with certain edge case integers, and so on. So as a result, we had a large set of disk images of all sorts of different formats that were manipulated in some way. Here we can see an example of the MBR partition table fuzzer. In the constructor, we set default values that are then used in the generate method to create an image based on these values. On the right hand side you can see the output of the fuzzer. So the fuzzer would replace this start CS value with 0, 16 and so on, and for each of these iterations it would create an image. So now that we had all those images, we had to find a way to check if Enkes Forensic Imager crashes when it tries to parse one of these images. And the most straightforward approach is to simply load these images into Enkes Forensic Imager and check if Enkes Forensic Imager crashes using the user interface. Since this doesn't scale very well because there are so many disk images that we had to try, we used an UI automation framework called AutoHotkey. We used a simple script to interact with the user interface and load an image, and then check if NCAS forensic imager crashes or not. This is probably not the best method to do this, but it was good enough, and within a couple of nights overnight we were able to manage to get all those images checked. What we were left with then, after checking for duplicates and so on, we found a couple of vulnerabilities. Most of them were simple denial of service vulnerabilities, so that when a forensic investigator tries to investigate an image, NCAS forensic imager will simply crash. These are the file system parsers that are affected, so X3, ISOFS, RISEFS, and the GPT partition table. We also found a heap-based buffer overflow in the parser for the RISEFS file system. This might be exploitable, possibly. And there is a stack-based buffer overflow in the parser code for the LVM format, and this is definitely exploitable. And I will now go a little into the details about this vulnerability and how we were able to reliably exploit it. First, if you're not familiar with the LVM format, LVM is a simple, or rather not so simple, abstraction layer that is used in Linux machines to abstract physical volumes, so partitions or disks, into volume groups, and from these volume groups, logical volumes can be spawned. These logical volumes are defined in this file that is stored in the physical volume, or rather a string in a header, and this is called the metadata. In this metadata, here you can see one volume group defined and one logical volume called test LV. So the vulnerability that we found affected the parser for this metadata string. Here you can see the pseudocode for this function. So the vulnerability affects the code that tries to get the name of the volume group. So in order to get the name of the volume group, this function first has to read the first line of this metadata file and then look in this first line for the curly bracket character, and everything before the curly bracket character is the name of the volume group. So here you can see the metadata line is the buffer that contains the first line of this metadata file. It then looks for this curly bracket character. If it finds it, it uses this memcopy to copy everything before this curly bracket into this buffer that are called overflow buffer. So as you can see, the metadata line can contain up to 1024 UTF-16 characters, while the overflow buffer can only contain up to 256 UTF-16 characters. So if the line is too long, a simple stack-based buffer overflow occurs. Here you can see what the stack looks like after an overflow occurs. So on the top you can see the source buffer of this copy operation, the metadata line. Then below there's this overflow buffer that overflows. Then somewhere below that is the stack cookie, the return address, and then the stack frame of the caller. Since there is a stack cookie, we can't just simply overwrite the return address and wait for this parseLV function to return. Because before it returns, it checks whether the stack cookie has been modified, and when we modify it, this would fail. But what we can also do is the parseLV function calls a pointer that is defined in an object in the stack frame of the caller. So before this function returns, it calls this pointer that is defined in the stack frame of the caller. So we don't have to rely on the return address, but we can instead overwrite this pointer and then modify our execution. So here are our conditions for exploitation. There is no ASLR enabled in this image. There is no control follow guard. Data execution prevention is active, so we have to use some sort of return-oriented programming. And the biggest restriction is definitely that we can only use UTF-16 characters. So if you would define this AAAA string in the metadata file, then we would overwrite the memory width for 100, for 100, and so on. So this is a very big restriction because we cannot arbitrarily overwrite memory the way we want it to. So the first thing we do is we try to move the stack pointer into a region that we control. And for this we use this gadget. It adds 5C to the stack pointer and therefore moves the stack pointer into this metadata line buffer, which is a buffer that we can control. And then we use our first rob chain to circumvent the UTF-16 restrictions. As you can imagine, it's really hard to exploit this vulnerability by only using UTF-16 characters. So the idea is that we load an unmodified rob chain somewhere into memory, or let the application load an unmodified rob chain into memory, find this rob chain, transfer execution to it, and we can then use this rob chain to fully control our execution. Luckily for us, the NCAS forensic imager doesn't directly copy data from the disk, so it doesn't directly pass data from the disk, so it doesn't directly read strings from disk, but instead it copies a couple of sectors into memory and then converts the data into UTF-16. So when the buffer overflow occurs, somewhere in memory there is unmodified disk content. And as it so happens, on the stack at EBP plus 18 hex, there is a pointer to a region in memory that is copied directly from the disk. This is where we place our second rob chain. Then we transfer execution to the second rob chain and can then exploit it. So here you can see the gadgets that we use. On the top you can see the stack. In the middle there is the memory region where the second rob chain is located, and on the bottom there is a memory region that contains the value 118 hex. We will need this in one of the gadgets. So first we set EAX to EBP, then we set ECX to this memory location, and we can use this memory location to add 18 to EAX, because this is a memory location that comes directly from the image and always contains the value 18. So we then use this gadget to add 18 to EAX. We now have the pointer that points into this LUM metadata header. Then we set ECX to this gadget. I will explain later why we need to do this. Then we dereference EAX. So EAX now points into this memory region. Also this gadget has a side effect that it overwrites this value. So in the next gadget we clean it up with 0 again. And now you can see the location is not the location of the ROP chain, of the second ROP chain. The reason for this is if we would put the second ROP chain at this offset for 0, then the application would no longer recognize the disk image as a valid LVM disk. So what we do instead, we at runtime insert the first gadget. So we insert this gadget here, then we transfer execution to this second ROP chain, and the gadget pops 3 values from the stack, and we are exactly at the second ROP chain. The second ROP chain is rather simple to generate because it's because the image is rather large, so it has a lot of gadgets that it can use. So mono.py does a really good job of automatically generating a working ROP chain that we can directly use. And Metasploit can then be used to generate the payload. And yeah, we can open calc. So the scenario that would be used by a criminal to exploit this vulnerability is, for example, to have a flash storage medium with incriminating data and simply add an additional LVM partition with this exploit. If anyone would ever try to gather evidence from this flash drive, the exploit would execute in Increase Forensic Imager, and the code that was provided by the suspect has full control over the investigator's machine. And it could then, for example, modify evidence or open a reverse shell or anything. So, okay, to the demo. Let's hope it works. So this is Increase Forensic Imager. By the way, this requires admin privileges to run, which is quite nice for us, because any code we inject runs also as admin. Then we add a device, and I've now connected a device through a write blocker. So this write blocker prevents Windows from modifying the evidence. So this is just to add more realism to the demo. So it warns me that the write blocker is in place. Yep. Again. Open. Again. Now I can use this functionality to scan for LVM drives. Whoops. And it's kind of a ransomware. Okay, so who's affected by this vulnerability or by these vulnerabilities that we found? Some of these vulnerabilities, for example, the denial of service vulnerabilities, not only affect the imager, so the free tool, but also the full forensic suite, at least in one version that we tested. And the stack-based buffer overflow that I showed the exploit for does not seem to be present in the Encase forensic suite. Here are just some guidance software's customers. We of course don't know which software exactly they use. So what can forensic investigators do to mitigate such vulnerabilities? As you might know, parsing binary data is always dangerous. So there's no there's no perfect way to prevent any of these vulnerabilities. What so good measures that forensic investigators do is they don't attach imaging machines, so machines they use to analyze evidence. They don't attach these machines to the network or to the internet, and also they use separate VMs for each case to avoid any cross contamination. But the problem is that the purpose of the imaging process, so the tool's main purpose is to create a trusted image. And as soon as an attacker can interfere with this process, the image can no longer be trusted. So the chain of custody is definitely violated if a code is executed while the imaging is in progress. So although those measures are a good idea to implement, they don't protect against such attacks. We, of course, responsibly disclosed the vulnerabilities to the vendor. The first couple of vulnerabilities, so the denial of service vulnerabilities and the heap-based buffer overflow, we found back in 2016, and we reported it, and they didn't provide a fix. So we released the advisory. You could argue, yes, we didn't have a working exploit to run code, so yeah, maybe they didn't care. The vulnerability that I showed you today, so the one that was exploitable, we reported this in March and also gave them the exploit, the working exploit that we wrote, and there was some communication back and forth, and they appeared not to respond. So when the release date that we set was coming closer and closer, we reached out to the executive team, and the response that we got was, we will get information if and when further information is available. So apparently they, I don't know, they didn't react to this vulnerability. So in March we released the advisory, but without proof of concept code. Through a journalist contact, we then got this great statement. They basically said this is an edge case that we found, and it has no impact on the performance or security, apparently, of the products. You can read this statement in its full epicness on our blog post, if you like. Okay, I think we have time for questions. Okay, thank you.
Please, yes. Are there questions? Yes.
For one question, can you please repeat why it is not necessary to override the stack cookie, so the basic exploitation?
Okay. We would normally override the return address to control execution, but NCAS Forensic Imager has a stack cookie, so an additional protection against this attack. And what it does, it has a random value. It stores it on the stack, and if an attacker would overwrite it, it would see this. So if we would want to overwrite this return address, we would also have to overwrite the stack cookie, because the stack cookie is before. And yeah, this cannot be done, because because of the stack cookie. So that's why we had another approach with this function pointer that was located in another stack frame.
And this was overridden too?
Yeah,
by
exactly. Yeah.
Okay.
So, any more questions? No? Then thank you very much.